Suppose x is a random variable associated with some random experiment. What if we repeat the random experiment over and over again? For example, suppose we flip a fair coin and record 0 if the coin lands heads and 1 if the coin lands tails. Let y be the total number of heads on 3 flips. Let's find the expected value of y, the expected value of y squared, and the variance. Since the coin lands heads or tails with probability 0.5, we have the expected value of x, 0.5, and the expected value of x squared to be 0.5. Then the variance is 0.25. Now, if we flip the coin 3 times, then y could be 0, 1, 2, or 3, and so we compute the probability that y is 0, 1, 2, or 3, and find. So our expected value of y is, and our expected value of y squared is. And so our variance is. Could we find the expected value of y, y squared, and the variance using y equal to 3x? Well, let's try it. We have the expected value of y. Well, that's the expected value of 3x. Expectation is a linear operator, so we can remove that factor of 3, and we get, which appears to be correct. Next, we have the expected value of y squared, which is, again, expected value is a linear operator, so we can remove that factor of 9 and get, and so we have, and we can compute our variance of y is the variance of 3x. We can remove a factor from the variance as its square, and we get, and these are different answers. So which one's correct? Remember, definitions are the whole of mathematics, all else is commentary. Using the definition, we found the expected value of y squared to be 3, so we should regard this as the correct value. But using the linearity of the expectation, we found e of y squared is 4.5. While this can't be the correct value, let's see why it didn't work. When we used y equal the sum of the 3 x's, the x's could either be 0 or 1, so we could get y equals 0, 1, 2, or 3. But if we used y equals 3 times x, the only x could be 0 or 1, so the only possible values are y equals 0 or 3. This means that in general we can't treat a repeated sum as a multiplication. And in particular, even though the distribution of x is the same for each of the 3 trials, we have to regard each trial as producing a distinct random variable. So y is really the sum x1 plus x2 plus x3, where the xi's have the same distribution but are not the same variable. Now before we continue, there's one last thing to address. Sometimes it's useful to consider doing things the hard way. So let's consider another approach. To find the expected value of y squared, we can compute the expected value of the square of our 3 independent variables added. We can expand. Now linearity still holds, and so by linearity, this expected value of x1 squared plus x2 squared plus x3 squared, well, that's just going to be the sum of the expected values of x1 squared, x2 squared, and x3 squared. But since all the xi's do have the same distribution, this is just 3 times the expected value of x squared. Likewise, this second part of our expansion will be, and again, these all have the same distribution, so this could just be the expected value of x1 times x2. But now what? And what this means is we'll need to look more closely at the expected value of a product. We'll take a look at that next.